In almost any factory, electric motors quietly do the heavy lifting. They spin fans, pump water, and drive conveyor belts to keep production moving smoothly. But physical systems are unpredictable. A heavy package might shift on that conveyor belt, wedge against the rails, and jam the entire line, stopping the machinery cold. The electric motor driving that belt doesn't have eyes. It doesn't know a box is stuck. All it knows is that it needs to turn, so it begins pulling more and more electrical power from the grid, trying to force the belt to move. This physical jam forces the motor to draw electrical current far above its normal safety rating for a prolonged period. This dangerous condition is what we call an overload. As a motor pulls massive amounts of excess current, that electrical energy begins to manifest as dangerous levels of heat. When the current forces its way through the motor's internal wire coils, it acts like the heating element in a toaster, driving up the internal temperature in seconds. This threatens the motor's most vulnerable component, the thin layer of insulation wrapped around those internal wires. Under normal conditions, this coating keeps the electrical current flowing in the right direction. But as the temperature spikes, that protective layer starts to bubble and melt. Once that insulation melts away completely, the bare copper wires touch each other. They short out, and the motor is permanently destroyed. To stop a physical jam from turning into a melted motor, the system needs a way to sense this dangerous temperature rise and automatically cut the power before the melting point is reached. That is where the overload relay, or OLR, comes in. You can think of it like a security checkpoint installed directly on the power line feeding the motor. The most common type is the bimetallic thermal overload relay. The term bimetallic just means the device relies on a special strip made from two distinct layers of different metals fused together. During normal operation, the regular flow of current creates a mild, perfectly safe amount of heat. The two-layered metal strip stays perfectly straight, and power flows to the motor without interruption. But during an overload, that flood of excess current creates intense heat. Because the strip is made of two different metals, the top layer expanding faster than the bottom layer when they get hot. This uneven expansion forces the entire strip to physically bend. As the strip bends far enough, it pushes against a mechanical trip contact. This snaps a switch open, which breaks the circuit and instantly stops all electrical power going to the motor. This clever mechanical reaction turns the dangerous electrical heat itself into an automatic emergency brake for the motor. This brings up a logical question. Every time you turn on heavy machinery, the motor requires a massive, temporary surge of power, often 6 to 10 times its normal current, just to get spinning. So why doesn't that startup surge heat up the metal strip and trip the relay every single time you press on? The solution is a feature called trip class, which acts as a built-in time delay mechanism. This chart shows exactly how that delay works. You can see the massive spike in current right at startup. Instead of reacting instantly, the relay is calibrated to wait a specific amount of time, usually 10 or 20 seconds, to see if that high current is just a temporary effort. If the current drops back down to a safe baseline before the timer runs out, the relay ignores the heat and the machine keeps running smoothly. But if a conveyor belt is jammed, that initial current spike stays high. The heat builds, the metal strip keeps bending, and when that time limit finally runs out, the relay trips the circuit. Trip class ensures the relay only punishes prolonged, dangerous exhaustion, while allowing the normal hard work of getting a machine started. While the mechanical metal strip is extremely common, modern facilities often use a digital evolution, the electronic overload relay. These devices discard the bending metal strip entirely. Instead, they use small microprocessors and dedicated sensors to mathematically measure the exact amount of current flowing to the motor at any given second. Because they don't rely on heating up a piece of metal, they don't lose energy to internal heat. This makes them highly precise, and they are an ideal choice for machinery that has to start and stop frequently throughout the day. Whether the technology relies on the physical bending of hot metal or the calculations of a digital sensor, the fundamental mission remains identical: monitoring the motor's workload to ensure it stays in a safe zone. When an overload relay does its job and trips the circuit, the recovery is straightforward. A technician clears the stuck package, waits for the relay to cool down, and presses a simple button to reset the system. However, new technicians need to understand a critical limit of this device. Overload relays cannot protect a motor against a sudden, violent electrical short circuit. If wires cross inside a machine and create an instantaneous, massive spike of electricity, you rely on a fuse or a circuit breaker. Those tools are designed specifically to break a circuit at lightning speed. The overload relay operates in a completely different domain. It is built exclusively to handle the slow, gradual burn of mechanical overwork. In a properly designed system, they act as partners. Fuses step in to block sudden electrical explosions, while the overload relay stands guard against a quiet, exhausting grind. We started with a simple mechanical problem. A jammed machine forces a motor to pull excess current, and that current rapidly turns into winding melting heat. The overload relay acts as the motor's indispensable bodyguard. It actively monitors the power line, bending or calculating in real time, to break the circuit long before that heat causes any permanent damage. By knowing when a motor works too hard for too long, this device saves heavy industry millions in broken equipment and lost production time.